In this lesson, we're going to look at the conservation of energy and energy conversions. So let's begin by being very clear about what we mean by the various different types of energy. You may have studied a little bit of this in earlier years, but perhaps not. Well, we break down types of energy into two main categories, what we call the action energies and what we call the potential or stored energies. If you look at the diagram, the action energies are things like light energy. That could come from the sun or from any light source like a light bulb or a torch. Kinetic energy, which is the formal name for movement energy. Sound energy. Heat energy, sometimes called thermal energy, and electrical energy that you get from batteries or from the mains supply. These are called action energies because each of them involves something happening or being done. Contrast that with the potential energies. These are all stored energies. So all of the potential energies are stored up waiting to do something. They haven't actually done anything yet. So they involve energy being stored in reserve for use at a later time. And the potential energies that you should be familiar with are nuclear energy stored inside the atom, chemical energy that occurs in fuels like petrol, for example. It also occurs in batteries. Gravitational energy. You can tell something has gravitational energy because if you let it go, it drops, so it gets its energy from somewhere. And there's also magnetic energy, although we won't have much to do with that. So we're going to make reference to these, and in the slides which follow, bear in mind the different types of energy that you've just met. I'm now going to introduce you to an extremely important concept in physics, and that is the law of conservation of energy. Energy is all around us. If you look at the picture, you can see a nighttime map of Europe, and you can see an enormous amount of light energy escaping upwards and being wasted into the atmosphere. Interestingly, although we refer to energy all the time, it's actually very difficult to define it. Even physicists have difficulty defining energy to say exactly what it is. So in practice, what we use is called an operational definition. We say what the energy does rather than what it is, because it's basically a lot easier. Operational is related to the Latin word opus, which means work. Since the Big Bang, and this may surprise you, there has never been a single instance of new energy being created. There has also never been an instance of energy disappearing. Quite remarkable when you think about it. This brings us to the law of conservation of energy, which states that energy can neither be created nor destroyed, merely changed from one form into another. And this is so fundamental in physics, it's very important that you memorize it. Okay, let's now consider some energy transformations where energy is indeed being changed from one form into another. The diagram shows a number of different situations in which energy is being changed from one form into another. So we have number one, a car driving along a road. Number two, a tree on a sunny day. Number three, someone hammering in a nail. Number four, an atom in a nuclear reactor. Number five, a food mixer in operation. And number six, a desk lamp switched on. What I'd like you to do is, in each of these 6 cases, write down the energy transformation or transformations involved as an energy transformation diagram. An energy transformation diagram is really very simple. You begin with the first energy, You then draw an arrow to the right, and on the right, you write down the energy that it changes into. Now, it could change into two different types of energy, but possibly not. So some notes. There may or may not be a third energy. It might just be energy 1 becomes energy 2. You have to decide. If there is a third energy, but it's very, very small, quite negligible, or it's kind of really not intended, then we often put the third energy in brackets. A couple of other things. Sometimes there's a whole chain of energy transformations and you need to know where to start. So when you're dealing with the car, start with the energy in the petrol. When you're dealing with number 2, the tree in the sunshine, start with the sunshine itself. When you're doing number 3, start with the hammer. And number 5, start with the power supply. And similarly, number 6, start with the power supply. So pause the video now and write down the energy change or changes for each of these 6 situations. Here is a reminder of the different types of energy you will need to use. Pause the video now and answer the questions. Right, let's see if you got them correct. So firstly, the car, the energy transformation is chemical in the petrol goes to kinetic as the car is moving. And because the car experiences air friction, as shown in the diagram, there's a little bit of heat. Well, if the car's going fast, quite a bit of heat actually. So chemical goes to kinetic, in brackets, plus heat. Heat's not really intended. It's a bit of a waste, but it is there. Number 2, the tree in the sunshine. Simple one, light from the sun changes into chemical energy in the tree. That is part of the process of photosynthesis, and it's how the tree gets its energy. Number 3, the hammer. Well, the hammer is moving, so it's got kinetic energy, and when it hits the nail gets kinetic energy as well, so there's no transformation of energy there, just a movement of it. But there is a change in energy as the kinetic energy of the hammer becomes sound and some heat. Heat is wasted, of course. Number 4, the atom in a nuclear reactor. The energy transformation there is nuclear becomes heat. There are some intermediate stages which we're ignoring, but in simple terms, nuclear energy becomes heat. Number 5, that's the food mixer. That's electrical becoming kinetic and a little bit of heat and sound as well. Heat and sound, of course, are not intended, so that's why they're in brackets. And finally, number 6, the lamp. Electrical becomes light, and there's usually a little bit of heat generated as well. With low energy lamps, the amount of heat's quite small. With older fashioned lamps, it's much greater. We now come to the final part of this lesson, and this deals with the energy transformation equations. Well, firstly, recall the law of conservation of energy itself. Energy can neither be created nor destroyed, merely changed from one form into another. Think about what that means. It means that if we can calculate the amount of energy at the start of some event or process using an equation, then the total amount of energy in joules at the end will be exactly the same as it was at the beginning. So even though the type of energy might have changed, the amount in total will still be the same. Now you'll be relieved to know there will be no new equations in this section. All we're going to do is use equations you've already met and use them to calculate the energy at the beginning and at the end of various processes. So we're going to give you an example to try to make this clear, and that's what follows. Okay, let's imagine we have a block of mass 5 kilograms and that it's lifted up through a vertical height of 4 meters as shown. Question 1, and I'd like you again to pause the video and answer these before proceeding. You can do these ones in your head, no calculations quite yet. So question 1, what is the energy conversion taking place? Pause now. Well, the answer is kinetic becomes gravitational potential. Question 2. Calculate the gravitational potential energy stored when the block is at the 4-meter height. Pause the video, take a pen, paper and calculator and work this one out. Well, you should know that gravitational potential energy is given by the equation EP equals mgh. So to solve this one in solution 2, we have EP is mgh, 5 kilograms times 9.8 newtons per kilogram times 4 meters, giving us a gravitational potential energy gained of 196 joules. So far, so good. So there's our block. It's been raised up 4 meters, and we now have gravitational potential energy of 196 joules stored. The block is now released and allowed to fall downwards, and it lands on the ground. Question 3. What is the energy conversion taking place? Pause and answer that one now. The answer is gravitational potential is changing into kinetic. Question 4. How much kinetic energy will the block have just before hitting the ground? Pause and answer now. Well, since all the gravitational potential has become kinetic, the block will have 196 joules of kinetic energy just before hitting the ground. And of course, you should know that that kinetic energy is given by the equation Ek equals 1/2 mv squared. So when the block was up high, 4 meters up, we had EP was mgh, which was 196 joules. And now that it's fallen and it's just about to hit the ground, the energy is now all kinetic. That's given by 1/2 mv squared. And that's the same 196 joules that we had at the top. We've made an assumption in getting to that answer. What assumption have you made in answering question 4? Well, we've assumed that all the gravitational potential became kinetic. That is, that no energy was lost to heat or sound due to air friction. So we now come to calculations. There's the scenario. The block begins 4 meters up with gravitational potential energy of 196 joules, and it falls downwards, all of the gravitational energy becoming kinetic, so that it has 196 joules just before hitting the ground. Now here's the sort of question you'll be asked in the National 5 course. Calculate the speed of the block just before it hits the ground. Pause the video now and see if you can work that out using pen and paper before resuming. Well, the way to do this is to realise that the kinetic energy at the bottom is 1/2 mv squared, and we know that it's 196 joules. So we just rearrange for V. So V squared must be the 196 divided by 1/2 of m, that's 1/2 of 5. So that's V squared is 196 over 2.5. That gives us a V squared of 78.4. Now don't make the mistake of thinking you've answered the question here, as many a pupil does. What we've got here is V squared, but it's V we're looking for, so we need to take the square root of 78.4, and we get 8.9 meters per second. So that block is travelling at 8.9 meters per second just before it hits the ground if it's released from a height of 4 meters up. The last question you just did is very like the sort of thing you would get in an SQA National 5 exam, and so is this one. If you have a look, you can see the same scenario, and the question is, does the mass of the falling body affect its final speed as it hits the ground? Now we're going to ignore air resistance, so there's no friction, so there's no loss of energy as heat or indeed sound. So ignoring air resistance and so energy losses, does the mass of the body affect its final speed? Does a larger mass end up going faster than a smaller mass, for example? Take a pen and paper, pause the video, and see if you can answer that question on your own. Well, here is how we solve it. First of all, we write down that the gravitational energy lost at the top equals the kinetic energy gained by the time the block reaches the bottom, just before it hits the ground. Let's put that into an equation form. mgh at the top equals a half mv squared at the bottom. Now, can you notice mathematically one of those terms is going to cancel? We can divide both sides by one of the terms and it will be removed from the equation. Well, it is of course the mass m. So we can divide both sides by the mass m and it cancels. And we're left with gh equals a half v squared. Let's rearrange that for the speed, because the question is all about the final speed of the body, and we get v squared is 2gh. Now it's v that we want, not v squared, so we take the square root of both sides, and we get that the final speed of the body always equals the square root of 2gh. That's the square root of the whole expression, 2gh. Well, what does that tell us? It tells us that because the mass m is not actually in the equation for the final speed v, then the final speed v is not dependent on the mass. So the mass of the body is essentially irrelevant. It doesn't matter what the mass of the body is. All masses will end up going at the same speed, neglecting air resistance, if they fall through the same height. The only factors that affect the final speed of the falling body are the gravitational field strength, that's which planet you're on, and the height of release. The mass of the body is irrelevant. And that's not an obvious feature of the situation. You need to understand the physics in order to see that.